Hello and welcome everybody to today's Hioki webinar. Today we're going to talk about expanding inverters, expanding on applications and measurements. I'm glad you could make it. As you know, our industry is changing dramatically right now. Silicon carbide and gallium nitride semiconductors make it possible to build devices that were completely unheard of just a few years ago. We're talking about efficiencies of really close to 100%. This requires new test methodologies. Techniques that were used for low efficiencies just don't apply well anymore. So in this webinar, we're going to explain to you the key challenge that you face when characterizing modern inverters. We are a test and measurement company, so we will be focusing on aspects of inverter testing. Characterizing inverters accurately is important for many reasons. You might be building models to optimize your system performance. You might be building inverters yourself and go through the usual engineering trade-offs. The world, as you probably know very well, is very different when you're hitting the 100% mark. Before I get into the technical details, let me do a few warm-up questions, a warm-up poll. We like to hear who you are and where you're coming from. So I have a few poll questions here. Let me start with the first question. Have you ever experienced more than 100% efficiency during your efficiency measurements? The answer could be yes or no, obviously. And the second question that I'm wondering about is if you have seen aliasing when you're measuring power. The third question, what switching frequencies are typically working with? Is this below 25 kilohertz? Is this below 50 kilohertz? Is this below 75 kilohertz? Or is that 100 kilohertz or higher? And lastly, what power levels are you talking about? What current levels are you talking about? Is this 10 amps, less than 10 amps? Less than 50 amps, less than 100 amps, 250 amps, 400 amps, or more than 500 amps. And I see some answers coming in already. Thank you very much for everybody who voted. Let me give it a few more seconds to make sure I get a chance to settle in and answer the questions. Okay. Thank you very much. Okay, let's move on. Let's stop the poll here. Thank you all for everybody who voted. So efficiency measurements, some of you, so about 1/3, have seen efficiencies or measured efficiencies that are higher than 100%. That's very interesting. Thank you very much. Yeah, we've seen that a lot with our customers. Have you seen aliasing? That's pretty much the overwhelming majority. 58% has seen aliasing, has had issues with aliasing, I presume. Switching frequencies, that is interesting. So majority of you are below 25 kilohertz. A quarter are at 75 kilohertz, and 8% are above 100 kilohertz. And then power-wise, it looks like there's a big spike at 250 amps, around 250 amps or below, and then pretty much evenly distributed from 10 amps to 500 amps. Well, thank you very much for participating in the poll. I really appreciate that. And let's advance the slides. I want to tell you a little bit about Hioki before we get into the technical details. The Hioki was founded in 1935. This is a few years before HP came into existence. We started out as a contract manufacturer. So we have a legacy of customer focus. Yeah, if anything contract manufacturers. If you're a contract manager, you know it very well. It's all about customer focus. We did a bold turn in the 1970s and started building our own instruments and focused on the electronic test and measurement industry. We are a fully vertically integrated company located in Japan. So all our manufacturing is done in Japan, not outsourced to low-cost countries. This means we have great control over all the manufacturing processes. We have been relatively immune to the component shortage so far. So that's something we are pretty proud of. We have about 200 main products that we have in stock continually, and we continue to innovate. So for example, during COVID, we released a record number of new products. I want to highlight that sustainability is very important for us. We have always been at the forefront of energy-related measurements, and that's really paying dividends for us right now. So our factory in Japan is certified to be zero emission. That has been certified in April in April this year, and we just got our certification as a green business from the city of Plano. Plano is a suburb of Dallas, where we are located in the US. So I want to just leave a few words about how we conduct the webinar today. There will be a moderated question and answer session, so we keep going. We will not interrupt the presentation for questions, but please answer questions as they arise. We have a panel of experts that will answer the questions as they come in. Use the Q&A box on the bottom of your screen. You can submit questions right there, and we will answer them as they come in. We will also summarize the question at the end of the presentation. So stay with us. The seminar is going to be just about an hour. The presentation will be recorded. So if you want a recording, let us know, and we will send you a recording a few days after the seminar is over. With this, it's my privilege and pleasure to introduce today's speakers. We have first and foremost Barry Bowling. Barry is an industry veteran. He has served in the test and measurement industry, both as applications engineer and as in marketing roles. His emphasis is on power analysis, memory, data recorders, and oscilloscopes. If you've worked with us in power electronics, power generation, electric motors, or hybrid vehicles, you've probably talked to Barry at some point in time. Barry holds a bachelor's degree in electrical engineering from the Georgia Institute of Technology, so a yellow jacket. Next, we have Naomichi Miyahiri. Nao-san has been working for Hioki for more than 10 years. He comes with an extensive background in test and measurement, in the test and measurement industry. He works as a product manager at Hioki USA right now out of the Dallas office. Nao-san holds a bachelor's of engineering in chemistry and a master's in engineering in chemistry from the Yokohama National University in Japan. Then we have our panelist. Our panelist today is Ishan Daljic. Ishan is an applications engineer for Hioki USA. He has more than 20 years experience in the test and measurement industry. Before joining us, he was a component test engineer with Maxim Integrated and an applications engineer for DFW Test, both of them located here in Dallas. Ishan holds a bachelor's degree in electrical engineering and electronic engineering from the Trinity College in Dublin. And myself, my name is Chris Schultz. I'm the product manager for Hioki USA. Before joining Hioki, I was product manager for Rohde & Schwarz North America, where I was responsible for the vector network analyzer portfolio. I do have a degree, a PhD degree in electrical engineering from the Georgia Institute of Technology. So now that you know a little bit more about us, and I want to pass the word to Barry, who's going to be walking you through the inverter testing, and I will see you at the other end in the question and answer session. Thank you very much. Barry, please take it away.
Chris, thank you. And Good afternoon to many of you, and good morning to some of you as well. We're going to talk about some semiconductor trends here in the first slide. So I'll be presenting a few slides, and we'll discuss challenges with measuring the new technology, inverters primarily, and then now Michi will follow up with the Hioki solution. So the SiC and the GaN market is growing 135% over the next 5 years. So that's about 20% per year. We've been hearing this for a little while, and Chris pointed out that the cost is coming down and the yield is coming up for these devices. So we're actually seeing truly more and more use of these semiconductors in inverters. And there's two types of inverters that are rapidly having SiC and GaN adopted into them. One is EV traction inverters. That could be cars, motorcycles, boats, a few airplanes, certainly trains, and a lot of agricultural, earth moving, as well as lawnmowers. So, and then also bidirectional grid tied inverters. I'll show you an example outline of that, but that would be a lot of solar or wind being tied to the grid. So SiC devices are expensive, but offer obvious advantages. In the case of an EV, increased range, power density as the components get smaller, less weight, and less loss heat. So that's the efficiency equation there. So that's happening. And the SiC and GaN applications will have higher voltages, higher currents, and higher frequencies. And just those three things alone will present challenges to properly measuring, say, the input power, the output power, all the parameters that you might associate with an inverter. Certainly the output is challenging to measure, and we'll focus on that today. So in the next slide, I'm going to look at an example of how a designer might choose, or why a designer might choose SiC or GaN devices. I want to start out on this slide too and just share two stories with you, just little war stories. Over the years, I've seen power analysis being pushed to the limit, and the equipment, the power analyzers and the power meters themselves, pushed to their limits. One of those includes the current transducer, sometimes called a CT. In the past, they were transformers. Less and less they're transformers, and they're more and more transducers, as in the FluxGate device that we manufacture. But the old school clamps were called Hall effect. They had a lot of bandwidth, reasonable accuracy, not the most accurate CT, used to some degree with scopes. But we saw those increasingly overheated. Our customers often couldn't tell us what they were doing to them. And this one particular customer in particular called and said, well, we nearly melted one. Can you tell us what happened? And I said, well, what happened? And they said, no, we can't tell you what we did. We can only tell you, we can only ask you, what do you think we did to it? They clearly didn't understand the spec. And I'll finish that story in just a few slides. They did something to it, and then they asked me, what did we do to it? So I'll tell you what I told them they did. The other story I wanted to share is one of greater than 100% efficiency. I've had that call many times over the years, and often it was something simple. It could be a wiring error. Some power analyzers are difficult to wire properly. Often it was something the customer never told us they did. But on a good occasion, I would get to visit the customer in person. I would build it into a trip and visit customers, and then promise them I could help them when I got there. So this one particular customer had a agricultural, just an earth mover, and they were designing and testing a traction inverter, and they had 120% efficiency. And they were running a power analyzer that sampled at around 2 mega samples per second. And the story wasn't that simple. There was a couple of phenomena going on there, and our troubleshooting process didn't end in one day. We were there 3 hours, and I took that problem home with me, and we studied it. And I'll tell you how I solved that problem with a colleague of mine in a few more slides. So here's what a designer may be motivated to do. They may be motivated to take this dual inverter design here, which has both a generator and a motor tied to it. This could be part of an automobile. And this step-up reactor and this battery, and make it all work better, go faster, run cooler, go further, and be smaller. And SiC and GaN can help him do that. Once he decides to go to SiC and GaN devices, silicon carbide, he can choose his switching frequency, the carrier frequency. So the carrier frequency is the switching rate of this inverter, whereas the fundamental frequency would be related to the speed of the motor. The fundamental might be 100 hertz, but let's assume that he's taken his old inverter design from, say, 20 kilohertz to 100 kilohertz, and he's going to make it smaller. Well, this step-up reactor that boosts the input voltage along with these input switches here, this reactor will become 5 times smaller if he increases his switching frequency 5 times. And you can tell looking at this, it's a high design. It's an expensive and heavy inductor. It's air core. It's intended to be as efficient as possible. And that's the reason for its shape. And that's the reason it's air core. So these take up a lot of room. So that's just one motivation. In fact, that's one of our target applications, is to help our customers take their reactor design and test it very thoroughly. Just test only the reactor. So anyway, there's just one example of what a designer might do and why you might choose 100 kilohertz. So I'm going to show you 2 quick application examples. The first one is a traction drive. This is an automobile or any kind of a vehicle with 2 motors. So this is 2 dynamometers. And because of that, it's an 8-channel application. And we have a solution for that. You'll hear about it later. But the things that we're facing at each of these inputs and each of these outputs is less obvious. So I'll state them. One is the harmonically rich complex waveform, mostly the voltage waveform, and not a trivial current waveform to deal with. In addition to that, those harmonics form harmonic power, and those pairs of currents and voltages will have very low power factor. And those very low power factor bits of power will be very challenging to measure, and I'll show you why and what kind of care is needed to measure those properly. I've said it, I'll say it again, we're facing higher voltages, higher currents, and higher switching frequencies simultaneously, along with the potential for aliasing. In addition to that, the higher switching speeds means higher, faster rise times, and that means more coupling into your voltage input and certainly also into your CT. So we'll talk about how do we manage common mode noise, both at the voltage input and now at the CT input. We need tremendous common mode rejection in order to keep those very fast rise times from coupling as false power or false current into the current transducer. This is the same set of challenges. It's a different application that is interesting to see because you've heard about it in the news already. It's been talked about in the paper for years, but basically at solar inverters, including at a residence, you'll see kind of a 4-way inverter. In the middle is a DC bus, and this enables power to go kind of whichever way we want it to go. They've got 3 bidirectional inverters in here, and then just 1 step-up inverter. So this is a lot of power analysis here. You may measure the input to the output here, and again, both ways on this one, bidirectionally on that one as well. But power obviously can go from the grid to storage, from the grid to the house, and also to charge the EV or to discharge the EV. If you had a storm, you might rely on your EV and your electrical storage to keep your home lit up and safe during that storm. It's the same challenges as the previous slide. Again, we're facing complicated waveforms and higher voltages, currents, and switching frequencies. So our agenda over the next few slides for me will be to share with you, I've narrowed it down to 5 things that I'd like for you to think about. And I'll share just a couple of slides on each of these issues: harmonics, power factor, the current levels, along with frequencies of those currents, aliasing, we've mentioned earlier, and then the common mode noise, or the DVDT, the rise time associated coupling into a CT. And then Naomichi, or Now as we call him, will propose a Hioki solution to you. So here we go, challenges to inverter measurements. The first one is harmonics. In the past, inverters had harmonics at 20 kilohertz. Maybe we were measuring 80% efficient inverter. We didn't worry too much about bandwidth or sampling rate, but all that's changed now, and it's due to the switching rate and the rise time of these waveforms. So on the voltage waveform, you see this is a semi-traditional PWM. It looks like a toothbrush. It looks like noise. When you zoom in on it, you see very fast rise times. These fast rise times create a lot of harmonic content in the frequency domain, and I'll show you that in the next slide. The phase current is a little easier to measure. It's a triangle waveform with fewer harmonics, and that's important, and I'll show you why. So these are the new waveforms we're facing. They're higher frequency and they're higher, faster rise times and fall times. So in the time domain again, is our PWM waveform. You can see how complex it is. And then here's our current waveform, almost sinusoidal, maybe not very challenging to measure. So that's good for us. The voltage waveform here, you can see in the frequency domain goes out past 1 megahertz. It's quite rich. Do we have to measure all that? The answer will be no, and I'll show you why. So primarily why is the FFT of our current. You'll notice that it falls off pretty rapidly. So in fact, if there's almost no current out here, there can't be any power. Even though we're producing harmonic voltage, once we multiply that times the harmonic current, we get near zero, infinitesimally small actual power being delivered to the load, typically a motor. So how many orders do we need? And are those orders based on our fundamental rate, or are they based on the switching rate? So they're based on the switching rate. The fundamental will typically be 100 or 200 hertz. The switching rate might be 100 kilohertz. And what we found, and I'll show you why, I'll show you how we found this out, is that current components that fall off above 5 times greater than the switching rate or the carrier are very small. And that, in fact, we believe that you need to measure to about the 5th harmonic of the switching rate. So let's do an experiment or a trial. Let's watch PN. Obviously, we'll watch the input power. You'll see that it doesn't really change as you give more and more bandwidth. But what we're going to do is apply a low-pass filter to an inverter's output, and we'll measure the power each time we change that filter. Where efficiency equals power out over power in, the graph I'm going to show you will change only as a result of the output power. So we'll track what happens as we change the filter. So here's a reminder. Our fundamentals here are going to have several harmonics that we will measure, and these have been easy to measure in the past with the older power analyzers. But now that SIC and GaN are on the scene more and more every day, we're seeing switching rates of 30, 40, 50, or 100 kilohertz. And here I've shown you 5 harmonics of 100 kilohertz, not by accident. So the trial that I did was on the 20 kilohertz switcher or inverter. And in fact, we applied a low pass filter that was guaranteed to show and capture power only of the fundamentals. So we call it the low frequency power of the fundamental rate. And then what we did was we opened the filter up a little bit and saw a little bit of increase in the output power again, and then again. And now we're measuring the first harmonic of the switching rate. So we're measuring the fundamental and up to and beyond a little bit, about 20 kilohertz. And then we kept opening the low pass filter up, and we saw that, in fact, our output power kind of leveled off here, so that we watched the efficiency, and this really could just be watts. We watched the output of the inverter to be measured from about 95% or 95 watts to about 98 and some change. So it went up 3 percentile points of output power or output efficiency. So that told us that we needed to measure to about the 5th harmonic of the carrier. As we continued to open the filter, that power leveled off. So that was just a trial, and it supported what we believed from what we saw on the FFTs. The typical load, challenge number 2 here, is going to be power factor. And at low frequencies, these motors have easy power factor. I'll show you a graphic for that. At higher frequencies, such as the switching rate frequencies and the harmonics of the switching rate or the carrier, this load looks very inductive. So this is a typical load of an inverter, and that's why we chose it. It's challenging to measure at those high frequencies, and it's easy to measure at the low frequencies. And why is that? Well, power factor is high. It's near unity or 1 in the low frequency region. That's easy to measure. That's easy for a power analyzer to measure. I'll show you why. Power factor that's near 0, where in fact the load looks mostly inductive, it's very challenging to measure in that high frequency region. Maybe you're measuring that at 50 kilohertz or 100 kilohertz. The frequency isn't the challenge. The bandwidth isn't the challenge. The challenge will be power factor. So on the left here, we've got a voltage and a current pair of vectors that are close together. This is a mostly resistive load. The angle between them is almost 4 degrees. And this is easy because this will tolerate errors, the errors that are inherent to measuring, but particularly errors that you might introduce with phase shift. And you're thinking, well, I'm not going to introduce phase shift errors. Well, a current transducer will. While the voltage waveform is easy to measure, introducing the magnetics and the electronics to measure that CT, you're not going to be able to use a shunt at higher frequencies. So don't think that. You're going to have to use a transducer, and you're going to introduce a small phase shift. It's inevitable. So just imagine that over here at 30 kilohertz, this angle is large. And you're probably thinking, well, the angle between the two is already large. What's a small phase shift error? Well, it doesn't really work that way. Even though this error, the phase angle here is fairly large, and 2 or 3 degrees would be insignificant compared to that angle. The next slide will show why. By the way, this is at 32 kilohertz, and this is a mostly inductive load. So here we're measuring, maybe it's the carrier or one of the harmonics of the carrier. Imagine that that's 100 kilohertz. So this last slide on the power factor challenge or the phase error issue will demonstrate to you why active power at low frequencies is easy to measure. So here we are with a high power factor, and just assume we're at several kilohertz, and that the S vector here, apparent power, it casts a shadow onto the x-axis, and that is your active power. Let's introduce a small phase error, several degrees, and that same shadow cast almost the same active power shadow onto the x-axis, and that is active power, and that is the relationship between S or S prime and the x-axis. That's the active power. The shadow is the active power. So that's a happy day, easy to measure, and that's where a lot of our power exists going into a motor. But there is significant power up at 30 kilohertz or 50 or 100. Here's an example of measuring one of those power harmonics. So we have S apparent power, let's say at 100 kilohertz. And here we introduced just a couple of degrees, maybe several degrees of phase error there on the current side. And that showed up in S, which became S prime. That shadow that we cast down here turned out to be more than 50% error on this active power vector. So I hope that's a convincing slide for you. What we have discovered is that for a voltage current phase difference of 89 degrees, a small error of only 0.1 degree will likely translate into an active power error of 10%. It plays well down here, 0.1% or 3% hardly matters, but 0.1% up at these higher frequencies and at these great phase angles matters a lot. Okay, the third challenge is our current and voltage input. So the SiC and GaN applications are falling into, they're pushing us into larger currents. That's application driven. These inverters might go into a train or even a plane. Submarines are starting to use them. So we're getting larger currents. We can make those currents manageable by increasing the voltage as well. So we're seeing requests for 1500 volts. Primarily 1500 volts is commonly a solar or bidirectional inverter voltage. and that lets us push trains. The more voltage you have, the more current you can use in your application to create that current. So, and then the EV traction inverters, we're seeing 800 volts, and those are rising as well. Those were 500 volts a few years ago, now 800 easily. So as voltages rise with the SiC and the GaN inverters, so do the current amplitudes. And as the currents rise, so do the bandwidth requirements. Designers are pushing current and bandwidth at the same time. My next slide, I'll show you a chart application-wise, how that's happening. So you're not going to be able to use, in this arena, you're not going to be able to use the old Hall effect clamps. You're going to be pushed into using a flux gate clamp, which is another type of zero flux current transducer. So in the next slide, we'll talk about safe operating area and the transient current overload question that we're getting now. I have customers saying, I know this exceeds your rating, but can I do it for 1 minute? Can I do it for 30 seconds? And then I'm going to talk about what heated the customer's clamp up here as well. And then where are the SiC and GaN trends taking current transducers? So when I got the call about the melted, almost melted, very overheated clamp, they sent it in and they let us run some tests. It was still working. We recommended they quit doing what they were doing and maybe to replace it. And they still couldn't tell us what they did. They asked us, what do you think we did? And we said, well, did you run it at 1 megahertz? So this is how frequency derating works. As you push further up in frequency, you know, in the design of a CT, you face issues. Bandwidth is one of those issues. Heat becomes one of the issues. These are derating charts based on ambient or room temperature. At warmer temperatures, warmer ambient temperatures, we want you to push less current through your CT. And then if you promise you'll only do this for 1 minute at these frequencies, we feel like you can be responsible and just watch the temperature of your CT. So we give you a 1 minute spec. And we don't do that on all of our CTs yet, but we're getting asked about it. And the frequencies I'm getting asked about are at 100 kilohertz or higher. And the currents I'm getting asked about at 100 kilohertz are several hundred amps. So we're thinking of how to help those customers. And for the melted CT, we feel sure that our customer just 100% hung that clamp at several hundred kilohertz or a megahertz, and then just left it there all day. And they were probably operating somewhere up here. And they promised to be nicer to their next clamp. So we said, okay, we'll sell you another clamp. So that's the answer to story number 1, what happened. So about this frequency derating chart, all CTs have this. They're based on continuous duty cycle, unless they say 1 minute. I have one spec on this same clamp that says just a few milliseconds. You know, you can hit some of these clamps at 3,000 amps for just a few hundred milliseconds. Let an amp engineer help you pick your clamp. The number that's on the side of your clamp isn't where you can run it all day. And there's no hardware that's an exception to that at these current levels, 1,000 amps or 2,000 amps. All of these things produce a little bit of heat. So there you go. There's where current and voltage inputs are headed. Let's see what that looks like in the application side and what it looks like with the type of device you're using. So this dark blue triangle, this is IGBTs, this is silicon MOSFETs. And a few years ago, we started getting SiC and GaN requests. As we moved up past a few hundred or a megahertz, we moved into SiC devices. These could be MOSFETs. And there's the train I mentioned. We've color coded this chart for our salespeople and our customers to imagine where just to save them time, what they should look at first. These clamps tend to be for scopes. These are Hall effect, and these are all flux gate, zero flux. They're all zero flux. These are the zero flux gate, high accuracy CTs and clamps. So what's happening is we're getting more and more phone calls out here, and we have products out here. Now Michi will show you a couple of new CTs that fall out here into higher frequency and higher current both. So that's one of the challenges, and that's certainly a trend. So in story number 2, I mentioned the 120% efficient traction inverter mystery, and we'll touch on that in these next slides with challenge number 4, aliasing. So in the time domain, aliasing, we've seen it many times. We sample properly our sine wave, and it's beautiful over in the digital domain. And then I'll intentionally undersample it here. And over in the digital domain, my power analyzer would see it as this much lower frequency sine wave there. And there's a problem with that. You might think, well, that's not going to bother me. The alias, I don't care about an alias. I'm trying to measure this blue waveform. There is a problem. And what will happen is that this waveform, because it's lower, will show up below the one you're trying to measure. And it'll certainly be included into your instrument's pass band. And it'll get thrown into your voltage or current calculation for a greater voltage or current. And it'll become false power in the algorithm of calculating power. Let's look at the same thing in the frequency domain so you can visualize that. This is our complex waveform along with its harmonics. Let's suppose we're using an older power analyzer that has a sampling rate here, that's and a Nyquist here, and we know that we shouldn't include anything into our A to D above the Nyquist. Well, let's do it on purpose and see what happens. And so there's the stuff we don't want. We need to filter that out because we can't properly sample it. Let's sample it, and there they are. They show up in our pass band. So now that's going to manifest as false power. So that 120% efficient mystery that I told you about earlier, part of their story was here. And part of the story will be in the next couple of slides. So one of the things that happened with that traction inverter test was aliasing. And I'll show you another graphic that'll explain that a little further. So the issue here is false power. This can cheerfully give you 110 or 120% efficiency. So what we need to do is sample it. Here's a brick wall low pass filter in front of the A to D. And also today's power analyzers, the modern power analyzers will have some anti-aliasing after the A to D, which includes oversampling and additional filtering. And certainly Hioki's doing that now. So anyway, here's a real world filter. As long as you use some anti-aliasing technique and you keep your sample rates high and appropriate bandwidth for your sample rate, you can prevent aliasing. And one of the first things you should think of when you see 100% or 110 or 110% efficiency, you should think about folding noise, which is where noise gets aliased into your waveform. Or you should think about outright aliasing that's occurring on the harmonics, especially with SIC and GAN. You're going to have a lot of harmonic content. If you undersample that, your instrument will cheerfully calculate it into its power measurement. Okay, so the remaining bit of challenges here is common mode switching noise. And for a voltage input, common mode rejection or CMRR is pretty easy to achieve. For a CT, it's not terribly difficult either, but it's been ignored for many years. And the reason was current transducers weren't faced with these rise times here. This is the enemy here. It's not the switching rate, it's the rise time and the fall time. And here's just an example. We've got a CT here. We're making a voltage and a current measurement here. And here's U1 is the voltage waveform from that step up converter in that schematic. And then here's ideally the current waveform. But in fact, using old traditional conventional sensors, what you'll find easily, and the CT guys, we all call this DVDT. This is the rate of voltage with respect to time. It's that rise time. So let's study real carefully. Here's U1. It's got a fall time, a falling edge. It's got a rising edge. In the same time frame, that falling edge manifests itself by coupling into the CT. It manifests itself as a glitch in the current waveform. And then subsequently the CT, which has a feedback loop, it tries to recover from that. And in fact, it has a little ringing there. There's no ringing on U1. This isn't just simple coupling. It's a very fast rise time that's forcing its way into the secondary of our current transducer. And the current transducer's feedback algorithm says that doesn't belong here. So it's trying to grab that and correct it and bring it back to what it knows is this ramp here. So this happens over and over and over again. And so in fact, with the agricultural tractor inverter that I mentioned earlier, this was exactly what was happening. The problem is we had a 2 megasample per second sample rate. So we didn't see this in our current waveform. It got aliased back into the passband of that instrument and then calculated as power so that the efficiency equation had output power about 20 or 30 points higher than was actually there. And it was partly the fault of the CTs. They were very low cost CTs. They weren't off-brand CTs. They weren't our brand, but they were just a low-end CT where no caution had been taken to give these devices common mode rejection. So I hope that graphic makes it clear that you need common mode rejection, not at 60 hertz. You need it at your switching rate. You need it at 100 kilohertz. This rising edge is going to blast through into your CT, and your CT is not going to like it. Here's what your current waveform should look like traditionally. And here's a spec, 150 dB. This is one of our very best CTs. It's a flux gate. It's a zero flux gate. And we've compared it against the old world pass-through type sensor. Okay, so here's another graphic. This is a screenshot of our PWM voltage waveform. And then let's go back to the general sensor. This is a generic sensor. It's got a lot of noise, and we've zoomed way out to be able to see that. So if you see that, that's U1 that's pushing into your current. You can try to filter it out. You probably should think about a better CT. And then these other two CTs, these are in fact late generation Hioki CTs. This is more like what your current waveform should look like in the presence of U1. So that's common mode rejection that you need for your modern power analysis of SiC and GaN. So very quickly, I'll review my challenges, and then I'll hand the presentation over to Naomichi or Now. I explained to you about measuring harmonics and why we need to do it to about 5 orders. For that, you need bandwidth, which means you need more sample rate as well. We talked about power factor. Now we'll tell you how we can fix that. We can correct that phase shift. So that's a rare feature, and you can't ignore high power factor at harmonic power elements. Then we talked about the rise in currents. And I kind of pointed out that you need to have an app engineer help you select a CT, or just study the spec sheet very carefully. And then we talked about aliasing, and I gave you a real world example of what I've seen with aliasing and how it manifested as 120% efficiency. And then similarly, we talked about common mode noise and what that looks like on a scope. And of course, the power analyzers have scopes. They have scope mode in them. And we have a poll coming up. So I'll introduce Chris to do the poll. Is that correct?
Hey, thank you, Barry.
Thank you.
So question that I have, measuring activity power, measuring active power near zero power factor is sensitive to what issue? Is that, I need to enlarge this windows a little bit here. When you have close to zero power factor, any measurement is going to be difficult. 89-degree angle voltage and current is difficult to measure. It's a very small amount of power and it's difficult to measure. A very small phase shift error causes small but significant error in the active power measurement. The second question, thank you all for responding already. How many harmonics of current and voltage do you think you should measure in the output of a signal inverter? Is this fundamental frequency is only sufficient, as many as possible, or 5 orders of switching power? And I give it just a few more minutes. Okay. Thank you, everybody, for responding. Okay, let's end the poll and share the result. Okay, so very small. So the first question, why is it so difficult to measure near zero power factor? Small but significant error in the active, the very small phase shift causes a significant error in the active power measurement. That is the correct answer. Thank you. I guess most of you got that. And then how many harmonics should you measure? Most of you think it's 5 orders, and that's the most common answer. I mean, if you're in research and development, you might sometimes want to capture many more harmonics. So I guess both answers are correct. So thank you very much for participating in this quick question. And I want to pass the word back to Now, who is going to tell us about how you actually measure and how you overcome the challenge that Barry described. Now, the stage is yours.
Thank you. Thank you, Chris. Let me move back to the slide. Okay. Okay, thank you, Chris. So we have seen 5 major challenges to modern inverter power analysis so far. Now we come to the next point, which is how we can overcome those challenges. So here I'm describing the challenges and solutions. The PW8001 offers a solution to the challenges we have seen. And for harmonics measurement, the meter is required to do high-speed sampling with high AD resolution. And also it is important for accuracy to be maintained over frequency. For aliasing, it's essential to use the power analyzers with high sampling rate. However, we cannot avoid high frequency components to be input to that meter. So power analysis engine 3 has an anti-aliasing filter to eliminate unnecessary high frequency components. For high current measurements at high frequency. So high current measurement is more difficult at the high frequency than at low frequency. So using current sensors fit for measurement requirements such as current levels and the frequency is essential as well. Hioki has been developing original wideband current sensors. And now we have been working on new current sensors to live up to emerging new demands. And power measurement with a low power factor is another challenge. So minimizing phase error is the key to achieve accurate power analysis. So the error, phase error increases in the high frequency for the current sensor. This is not avoidable. So the PW8001 implement auto phase shift function to correct the phase error. So this function this is the first equipment to do phase error correction automatically. And the last point is common mode noise. The common mode noise is likely to be coupled. I'm sorry. Coupled with voltage measurement lines and the current measurement lines. And the meter per se is highly immune to, should be highly immune to common mode noise. So PW8001 installed aluminum case and optical isolation. So these two technologies increase CMRR, or common mode rejection ratio. So the common mode rejection ratio is 120 dB at 50 and 60 hertz, and 110 dB at 100 kHz. So we can confidently do accurate power analysis with the PW8001 and current sensors. Okay, so next I'm going to move on to solutions more in detail. But before that, I would like to touch on the PW8001. So this is our new power analyzer, which is released next month. So this power analyzer, you can install 8 different modules, and we will have 2 types of input module. One is for high voltage applications, such as photovoltaic applications. And the other is specially designed for high-speed applications, such as GaN and SiC inverters. So again, this meter offers up to 8 channels, not 7 or 6. The channel count of 6 or 7 are very typical for existing power analyzers available in the market. So 8 channel is the maximum channel count. So you can create the configuration you want freely with this meter. So the next point is the input module. The U7005 is high frequency input module, which offers highest accuracy and the highest sampling frequency, and widest bandwidth up to 5 megahertz. So accuracy-wise, the DC accuracy and the 50 kilohertz accuracy is much superior to existing power analyzers available in the market. So you can do most accurate power analysis with this input module, with minimizing harmonics measurement issue. So this is the input, but besides that, the meter has excellent power analysis engine. So this power analysis engine 3 has 2 anti-aliasing filters to eliminate unnecessary high frequency component. So Depending on the level of input signals, the engine set most appropriate range automatically. And then signals are filtered with anti-aliasing filter, and analog signals are converted into digital signal with a phase correction, or automatic phase correction, to minimize phase error of current sensors. And after that, 4 different processes are carried out simultaneously. So 2 of them have filters. One is a zero crossing filter. This is a critical element for accurate power analysis. So for accurate power analysis, detecting one cycle precisely is vital. So this zero crossing filter is applied automatically, and you can do power analysis without changing settings. And also, digital anti-aliasing filter is placed just before harmonics analysis. So, so this filter, of course, eliminate high frequency components unwanted. So you can see in this graph, in this diagram, 5 odd functions. So this power analysis engine 3 is most suitable for inverter measurements with variable speed control. So you can confidently do power analysis with this engine. Okay, I discussed the power analyzers, the new technology, but in addition to it, we have redesigned the current sensor series. Here you can see our current sensors, path-through current sensors, and application. So I would like to point out the CT68, 73, and 72. These are designed for high-speed applications such as GaN inverters. The frequency band of them is 5 megahertz and 10 megahertz. These new current sensors are automatically recognized with the meter. So for different pieces of information read by the meter automatically, which are phase shift correction point, sensor model, a rated current, and a serial number. So this automatic recognition enables auto phase shift function. So this function is 100% automatic function. So once you connect the current sensor to the meter, this function works immediately. So plug and play function, no calibration and external device are required. So here you can see phase response characteristics, and red line is the original current sensor's phase response characteristics. So from 10 kilohertz, the error is increased, and the automatic phase shift function corrects the error, and the line is changed to yellow line. So you can achieve a flat frequency response. And the last point I would like to point out is CMRR, common mode rejection ratio. So Hioki path-through sensors use solid shooting case, which reduce CMRR. So as you can see, the blue line is CT6904's CMRR characteristics. This sensor achieves over 120 dB at up to 1 megahertz. This is extremely higher than conventional sensors. And the graph on the left-hand side is the actual waveforms. You can see CT6904's waveforms don't include high frequency components. So Hioki pass-through sensors minimize common mode noise for accurate current measurement. Okay, this is my last slide. I pass it back to Chris.
Hey, now, son, Barry, thank you very much. So let me wrap up quick the presentation part before we get into the question and answer session. I've seen a few questions coming in already. Electrification is happening rapidly, faster than we expect. We see it everywhere. It's driven by GaN and gas technology. As Barry pointed out, it enables high efficiency converters. It requires new measurement technology. You're running into all sorts of challenges. We mentioned 5 of the main challenges. That is harmonic content. So we see much higher frequency, higher switching frequencies. We've seen more harmonics. Power factors becoming an issue, like Barry showed. The motors start looking more like inductors when you go to higher frequencies, which makes it more sensitive to measurement errors in the current. We have to deal with high voltage, high currents. We see in 1500 volt systems, 2000 volt systems are coming up in the not so far future. Aliasing, like you said in the introduction, is something that I think 60% of you have experienced already, which can get grossly wrong results, like Barry showed in one of his customer interactions. And common mode, which makes the current measurement susceptible to noise. You have high switching voltage, high currents, you have a lot of noise there. So we built the PW8001 to address these issues. We want you to focus on building better inverters and not building better test tools. You can reach us. We are in Dallas, in Plano, suburb of Dallas. We have a facility there that just got certified to be 17025 compliant. We have a support and service center there. You can reach us by phone, by email. You can, of course, check out our website. We are active on Facebook, YouTube, Instagram. And with this, I'd like to move on to the question and answer session. So if you have any more questions, please type them in. We're gonna answer them right as they come in. What I've seen here, the first question I've seen coming in is, okay, somebody asked about a bit more background information. What makes these new SiC and GaN devices more efficient than silicon devices such just as MOSFETs and IGBTs? Barry, can you say a few words about that?
Yeah, Chris, thanks. So in the past with the silicon devices, there are some lesser losses, but the two primary losses were turn-on transition and turn-off transition. And that's that short period of time during where your device, whether it's a MOSFET or a bipolar or IGBT, that's where it's transitioning from off to on and then from on to off. It's linear in that region and it produces heat, and that's your waste. And that period of time was pretty long with silicon. That period of time is short or fast. It's a very short duration with SiC and GaN. Also the turn-on resistance has been lowered quite a bit with these new devices.
Barry, thank you. Thanks for the insight. Next question I have, here's an interesting question. Somebody's going all out. So is your new instrument, the PW8001 we call it, will your new instrument also work with diamond powered electronics or diamond power electronics, I think it means? Barry, can you say something about that?
Yeah, I haven't seen a lot of calls from, or almost no calls from the guys using diamond substrate yet, but the challenges will be the same. If those devices run faster and the switching times get even shorter and it gets even more efficient, we'll be there. We'll be ready to measure it. So it's really the same test.
Thanks, Barry. Next question that I see here: how can you correct for phase shift of your current sensors without a reference measurement? And that's an interesting question. Now, Son, I think you can talk about that, right?
Sure, I take it. Okay. So we Hioki are the only manufacturer of power analyzers, and we make our own current sensors, and we have very tight control of the manufacturing process. And in contrast to all other current sensors on the market today, our zero flux current sensors have a smooth phase roll-off. So more importantly, the phase roll-off is very stable and reproducible. For the reason, we are able to compensate for frequency and phase roll-off of our current sensors, and we do not need reference measurement. So just for PW8001, what you need to do is connecting current sensor to the meter, and the phase shift correction point is automatically set. So sorry, my answer is long, but the short answer is we don't need reference measurement.
No, Son, thank you very much. Yeah, it's pretty exciting technology that's in our power analyzers. Here is one more question: current phase shift differentiate from IV skew, perhaps? Yeah, it's the roll-off, the phase roll-off over frequency that we're talking about, right? It's not just a skew. It's the spectral variation of the phase. The spectral variation of the phase, and which typically is a roll-off. If you look at some current sensors, they go all over the place. Yeah, ours are very smooth, so we can compensate them without a reference measurement, which is what now just explained. So thank you much. Those are all. Oh, here's one more question. I have a few questions actually. Will the recording be available? Yes, we will make the recording available to you all. Send us an email that you want the recording. We send you a link. It takes a few days until we edit it and are ready to put it out. So send us an email and we'll be happy to send you a recording of that webinar. And so those are all the questions that we had. I thank you all for staying on. We went a little bit over. Exciting times, exciting technology. So thank you very much for doing that. Wanted to thank our team, Ishan, Nausan, Barry, and of course, Jennifer behind the scenes for putting this webinar together. And I wish you all a wonderful rest of the day. Thank you very much.